Hello and welcome to this question having a look at applied halogens. So the application here is matching observations in displacement reactions between halogens and halides with the reactivity trends that drive those observations and what actually causes the reactivity trends themselves. So looking at the question, you can see that you've got some information at the top describing what a student does in terms of the actual chemical reaction. You've got the observations that they've recorded and also some instructions on what they want you to do in terms of explaining all of this. So looking at the instructions first, there are three things to do. You need to explain how the student's results provide evidence, you need to write an ionic equation, and you need to use your chemical knowledge to explain the trend in reactivity. There's no particular order in which these come. I'm going to choose to put three different subtitles down and try to use those to sort of focus my mind when I'm constructing my answer. So looking at what the student has done, let's take each step in turn. So bromine is in the form Br2, so is the unreacted halogen in this question. It says it's an inorganic solvent, so I'm not going to worry about trying to think about how to write a state symbol for that because there isn't one. So it then says that the student adds aqueous sodium chloride to one test tube and aqueous sodium iodide to the other test tube. So that now means that the organic solvent with the bromine dissolved in it is now in the same test tube as aqueous sodium chloride in test tube 1 and is in the same test tube as aqueous sodium iodide in test tube 2. So I've just kind of visualized that by writing it down there. So the organic layer, remember the organic solvents that we use are non-polar, so therefore they will tend to dissolve the non-polar halogen molecules better than water will. So this will indicate which halogen remains, either as it's been displaced or if there was no reaction in the first place. So thinking about the reactivity, you can consider a number of different factors: atomic radius, number of shells, shielding, oxidizing ability, as referred to in the graphic that I've put into the screen there, and any nuclear attraction for potentially gained electrons. So the first thing to do is to state the trend: chlorine most reactive, then bromine, then iodine. The organic layer is orange due to bromine, e.g. no reaction between bromine and chloride ions. The organic layer goes violet in the other test tube because iodine is displaced by bromine, reacting with iodide ions. So going down the group, the atomic radius increases, meaning more electron shells, more shielding, a decrease in nuclear attraction for any incoming electrons, so therefore the oxidizing ability or the ability to gain electrons from other species goes down. So to think about the ionic equation, you start with the balanced equation and you look for the spectator ion or ions. In this case, it's going to be sodium or Na+. So you get rid of the sodium on both sides, and that allows you to write 2I- plus Br2, giving you 2Br- plus I2. I'm leaving out state symbols at this point because I haven't asked before them. So let's have a quick look at the mark scheme and analyse what it says. So first of all, you include all observations and interpretations for your first marking point. It doesn't matter if you don't put the ionic equation second, you can put it towards the end of your answer if you wish, it'll still be credited, but it doesn't have state symbols and you can see that they've told you to ignore state symbols. So I think the reason for this is because one of the species, or two of the species rather, the bromine and the iodine will be dissolved in organic solvent, and that will cause a bit of confusion for people if they try and come up with a state symbol for that. So looking at the actual the bulk of your explanation, you need to link reactivity in terms of either oxidizing power, gaining electrons, forming a negative ion. So those two need to go together for your first marking point for reactivity. And that needs to be sort of connected to size or shielding of shells, which then leads to nuclear attraction and becoming less down the group. So just moving over here, there's two things there that are also relevant, but they just don't go far enough in terms of explaining what's going on. So it says to ignore them. So it says don't allow the idea of losing electrons or ionization energy because halogens don't lose electrons when reacting, so that's technically wrong. That's actually what happens when metals react and you're dealing with non-metals here. Okay, so hopefully this gives you a little look at some of the nuances of this particular question and some tips for possibly how to put together a reasonable answer. Again, thanks for listening. Until next time, see you soon.